This presentation is delivered by the Stanford Center for Professional Development.
So let's go ahead and get started with the actual content. And so today is the day where we make a little bit of a transition. It's like one of our transition points in life. It's kind of like coming to college. And the transition point we make is you now come into the Java world. And you're like, but I'm still doing Carol. Yeah, well, in lectures, we're going to sort of wave bye-bye to Carol. And Carol's like, yeah, I'll be there in your dreams when you're actually programming, right? So Carol's not really gone until you're done with assignment number 1. But now we sort of graduate into the world of Java. And you'll actually see a lot of the things that exist in Carol's world will come back because we give them to you in the gentle form in Carol's world, and then in the Java world they come full steam. So before we dive into that, I want you to get a little notion of the history of computing. Okay, and we'll go over this very briefly, but computing actually has a very long history, and it dates back about 4,000 years. Okay, so roughly 4,000 years ago, the first what we think of as computing device was made available. Which anyone know what that was? Abacus was the first computing device, and allowed you to do some fairly rudimentary arithmetic on it, but it actually was something that allowed people to compute a lot faster than they could by keeping track of stuff in their head. The real sort of advances in what we think of as computing actually came around in the 1800s. There was someone by the name of Charles Babbage. Anyone heard of Charles Babbage, by the way? Just a quick show of hands. We can just call him Chuck. He was actually a very well learned and well-known person in his day. He had the Lucasian chair, which is the same chair at university that actually Stephen Hawking has now, that Sir Isaac Newton had at one point. So, pretty smart dude. And he came up with this notion of something called the difference engine, which was a way of being able to automatically, in those days, right, they didn't have silicon, they had silicon, but it was in the form of sand. And they didn't have computers in the way we think of computers, so he wanted to build a mechanical device, like with real, actual, mechanics and pieces of wood that would spin around. That would, in his time, he thought it would be powered by steam, right, because this is sort of pre-thinking about electronic computers. That would do automated calculations. And he designed something called the difference engine, and then he designed something called the analytic engine, which was supposed to be even more powerful. And interestingly enough, neither one of them were ever actually built during his lifetime. It turns out that years later, the difference engine was actually built from a bunch of wheels and rotors and stuff. And now the thing that he would have liked to think of as the analytic engine, we think of as these puppies. It actually turned out in the 1800s he had a lot of the same ideas that are in our laptops or in our computers today, strangely enough. But so that's kind of where computing, we think of the notion of computing as really coming from. And it turns out the first programmer was a woman by the name of Ada Byron. Actually, Augusta Ada Byron. And if the Byron looks familiar to you, it's because she was the daughter of Lord Byron, the English poet. And she was actually very taken by the designs of Charles Babbage's machines and actually wrote programs. The machines were actually written to have sort of cards, sort of like the Jacquard loom, if you've ever heard of the Jacquard loom, and if you haven't, it's not important, that actually would have programs for the kind of computations that it would do. And she actually devised various programs for Charles Babbage's analytical engine. And you might be sitting there and you might think, but Mehran, you just told me that the analytical engine was never actually built in their lifetime. So what's she doing writing programs for a computer that doesn't exist? And that's actually something that happens today. People write programs for computers that don't exist. And you might wonder, why? That's like not a very good use of your time. Well, guess what? If the next generation of computers is going to come out, while it's still being designed before it's actually manufactured and built, someone needs to figure out what kind of programs you want to run on that machine. So there are actually programmers today who write programs for machines that aren't built. And they simulate them by hand, and they go through and try to figure out what they would do, and it's a perfectly reasonable thing to do. But as a result, Ada Byron is, in some sense, the first programmer. Right? Because she was actually writing programs for, in some sense, a general-purpose computational device over 100 years ago, which is kind of an astounding thing if you sort of think about it. Now, it turns out computing actually got its first real, what we think more closely of as computing devices in the 1930s. I should put 19 here just so we're clear. 1930s and 40s, there were sort of the first prototypes of electromechanical computers that were actually built at the time. There was a computer that was built at Iowa State by Adanasoff and Berry. The names are actually not, well, they're important if you're a lawyer, because it turned out there were actually lawsuits at the time about who patented the computer, but we won't talk about that. Started sort of in this era with sort of prototypes, And then the one machine you may have actually heard of by 1946, there was a machine called ENIAC, which was actually built by Eckert and Macaulay at UPenn, which was standard for, if I can remember this, Electronic Numerical Integrator and Calculator. And basically it was one of these big things that, sat in a big warehouse, a few tons, but it actually did computational, the kinds of things we would think of as computation. And it was really, in some sense, the first large-scale electromagnetic computer that we think about. Again, modulo lawyers. And then, really, it was in 1971 that the first microprocessor came around. So we come to a fairly modern time, right? So it's not all that long ago, like we're talking 36 years, that microprocessors have actually been around. And so the first microprocessor, and one of the folks who was on that team who built the first microprocessor, Ted Hoff, is actually a Stanford alum, interestingly enough. It was built at Intel. The Intel 4004 was the name of that microprocessor. And at the time, no one actually thought that having the single-chip microprocessor was going to be that interesting. He sort of designed this thing, and it was originally going to be going over for use in some machine in Japan. And they were just going to give them sort of the design and the patent for it. And the folks who were getting it were like, well, we're not really interested. Yeah, sure, it's an interesting chip, but we're not actually interested in owning the patent. We don't think there's anything interesting necessarily here. And so they kind of ran with it. And the rest is history, as they say. And as you can imagine, the last 35 years or so, there has just been an astounding amount of development in computing and computer science, right? So really, this field is like hundreds or thousands of years old, if you think about it. But really, it's kind of in your lifetime that all the interesting stuff is really happening. Which is also why it's exciting to be alive now and be a computer scientist, because you're in this acceleration phase, right? Think about what's going to all the stuff that happened in the last, 36 years. You're going to be around to see the next 36 years, and you're going to be doing the next 36 years. So that's just an exciting thing that I think about. But another thing that comes up when you think about this is, what is computer science, right? Why do we, we've been talking about Carol programming, and a lot of this class we're going to learn about software development and Java programming. And so a lot of people tend to equate computer science with programming, and they think, well, why isn't the major just called, computer programming? And why is there really a science to it in some sense? And that's something that people actually would use to debate. They don't really debate it so much anymore. Is there a real science of computing? Or is it just programming? And in fact, the difference between the two is that computer science, or CS as we'll just affectionately refer to it, really is the science, or in some sense the study, of problem solving with computers. And you don't need to write this all down. It's just for your edification. With computers, or I should say computational devices. Computational, I'll even say methods, because some people actually look at, theoretically what's possible to compute without even necessarily thinking that it's realized in hardware, right? Turns out it actually surprises people. There are some functions that you can prove are not computable. They're like, what, really? You can? Yeah, and it's good to know about them before you go and try to write a program to actually compute them, because in theory they're not computable, and you can prove that. And if you're actually interested in that, take CS103 or CS154, and we'll talk about it all the time. But that's really what the science is thinking about problem solving and the approaches to problem solving, how you analyze how efficient a solution is to a problem, how solvable it actually is, the different approaches you take to it. So notice the word programming doesn't show up here. Programming is an artifact. It's something we do to realize that particular problem-solving technique in a computer or some computational method. It's just something we do as part of the process, right? It's not what the whole thing is really about. In some sense, there's actually this famous quote that computer science is just as much about programming as astronomy is about building telescopes. Right? Astronomy is about far more than building telescopes. It's really sort of the science of celestial bodies. Telescopes is the mechanism by which you actually look at them. Question in the back? Well, if you think about computer engineering, part of it's just kind of the definition that a particular school wants to have for it, right? And some places actually, our computer science program is in the School of Engineering. Some places it's actually in humanities and sciences. It depends on the view, and it also depends on the particular program that's there. So some places may actually, there's no way I'm going to hit you in the back, may just be training programmers. Right? And the science of computing is not what they're actually interested in. And so it depends on the program. But we really think of computer science as a science. And it's an interesting philosophical argument. We can certainly talk about it more in class, but I just want to kind of push on. All right? So with that said, that's kind of the quick tour of a couple hundred years of computer science history. It turns out when we get into modern day, when we actually think about computing, what does a computer really understand? And what are the programs that you write on it, and how do they turn into something the computer understands? So it turns out the computer actually only understands zeros and ones. And so we like to think of that as binary. right? Binary is just a number system that only has zeros and ones. It's base 2 numbers, basically. And that's all computers understand, zeros and ones on and off. So how do we take these things like move or turn left and turn them into ones and zeros? And so there is something called machine language that is what a computer understands, or in some sense what the microprocessor understands, right? The machine language is defined by what chip you have inside your computer. That's eventually going to boil down into a bunch of ones and zeros. People are real bad at writing ones and zeros in a form that computers can understand. So we program in what's known as a high-level language. Okay? And there's all kinds of high-level languages. So one of the ones that you're going to learn in this class is Java, and there's some other ones you may have heard, like C or C++ or BASIC or Fortran or whatever the case may be. These are all high-level languages because they're at a higher level than what the machine understands. And so there's this question that's actually part of the science of computing is, how do you go from this high-level language into something the machine understands, right? What is this translation process? Because there actually is some translation that needs to happen. And this process, going from the high-level language to the machine language, is something we refer to as compilation, right? So compilation is something, strangely enough, that's done by a compiler. And Eclipse, which you've been using this whole time, is in fact a compiler. It takes the instructions that you write in some high-level language and converts them into some form that the machine understands. Now, it turns out the process for doing this in some languages is actually slightly different than other languages. So I want to show you a quick little overview of how that looks in Java, just so you can get a real sense of what's going on between the time you write a program and the time the machine executes it, so you sort of understand it at a low level. As programmers, you write what's called source code. Know it, learn it, live it, love it. Source code. That's what you're going to write. When you were writing Carol programs, you were writing source code. When you write Java, you're going to write source code. What the machine understands, these zeros and ones here, is something that's called object code. And object code is essentially just the low-level instructions, the machine instructions that the computer understands. And so going from source code to object code is basically what the compiler does. It's the translation from this to this. Now, in regular languages, that might look, if we got the overhead, I shouldn't say regular languages, in some classical languages, it might look something like this. You write some source code in what we refer to as the source file. A source file is just a file that contains source code. So you write your program, that goes into some compiler, let's say Eclipse, which is the compiler you're using, and what might come out of it is an object file, because what's contained in that file is just essentially object code, or in this case, a bunch of zeros and ones that the computer understands. And there might have been other programs that someone wrote along the way, like some libraries you might make use of, like you did with Carol, right? All the basic Carol functionality might be in some other library. And so there's other files that contain object code. And all of this stuff gets linked together into one big set of object code, which we refer to as the executable, or the application. That's the thing that, say, when you double-click on your word processor on your computer and it runs, you're running some executable file, which is just basically a file of a bunch of ones and zeros that eventually, or some time ago, someone wrote a source code and got compiled down in this executable file. And for a lot of languages like C or C++, this is the process that actually happens. Now, the people who did Java thought of things slightly differently. And here is kind of where things get funky in Java. Okay? In Java's world, part of what's going on is actually run on a virtual machine. What does that mean? It means you write some source file in Java, okay? That goes through some compiler, and what comes out of it is not an object file, but something called a class file. It takes all of the high-level stuff that you write in Java, or in this case you could say Carol, because it's the same thing, and turns it into some set of numerical instructions that are not yet ones and zeros that the computer understands, but are some intermediate language that's just a numeric language. Okay? Sometimes we refer to this as Java bytecode, but the name is actually not important. It's some intermediate language. And guess what? There's other classes, just like there were before, that contain instructions in this intermediate language, and those all get linked together in some big file that we call a jar archive, which just stands for jar, just means Java archive, strangely enough. So it's actually redundant to say jar archive. People just do, but it means Java archive archive. All right? And then this whole thing is now a set of this intermediate language, which is something that neither the human really understands. Okay, there's a few humans in the world that might, and they're a little weird, and we won't talk about them. Most people don't understand this, and the computer doesn't understand it directly either. So you say, well, that's the most useless thing ever. Why would I ever do that? These instructions go to something called the Java Virtual Machine, the JVM. And what the Java Virtual Machine says, it says, hey, guess what? I'm going to be pretending like I'm a machine that understands this as my object code. I understand this stuff as the basic language I speak. And I take that, and when I run it, I do something on your computer. And you might say, why would you want to have this extra process? And the reason why you want to have this extra process is the fact that, guess what? In the world, there's things like Macs, and there's PCs, and there's Linux computers, and there's all kinds of machines out there. Which means if you sort of do things in either the good old way or the bad old way, the compiler needs to understand what are the ones and zeros that your computer speaks. And the ones and zeros that a Macintosh speaks are different than the ones and zeros a PC speaks. And they're different than the ones and zeros a Linux machine speaks. So the compiler needs to know all that if it's actually going to generate this kind of code for all of those different sorts of machines. And most compilers don't. Most of the time you get a compiler and it says, hey, I'm a PC compiler. I'm just going to generate stuff for the PC and that's all I do. In Java's world, things are a little bit more interesting because the compiler doesn't need to know what kind of computer you're running on. It says, hey, I'm producing this intermediate language, and the intermediate language is the same for all computers. The only thing that has to be different on your computer is you need to have this little thing called a JVM that knows how to translate this intermediate language into what's going on your computer. So if you have a JVM for your Mac, or a JVM for your PC, or a JVM for your Linux machine, they can all run the same low-level intermediate code and do the right thing on those computers. Okay? And so remember when you set up Eclipse, or if you haven't set up Eclipse yet, you'll get there soon enough, but when you were setting up Eclipse, we asked you to download and install something called the Java Runtime Environment. And how many people remember that? Raise your hand if you remember that. A few folks. Guess what the Java Runtime Environment provided? It provided this thing for your computer. Okay? So you write the program once, you compile it once, and now that class information that you have, that class file, can be run on any computer that has this Java virtual machine. And Java virtual machines are sort of ubiquitous. They exist for a lot of different computing platforms. Okay? So that's why they actually do it that way. And it's kind of funky, but it's a little bit different. Now, with that kind of said, that's the low-level stuff. That's kind of what's happening at the low level. And you don't really need to know the low level intimately. I just want you to understand what's happening from the programs you write to what happens when they get executed on the computer. Now, what you do need to know is how do we begin to write programs in Java. And Java, you'll see some examples of it today, is what we refer to as an object-oriented language. Okay? So Java is object-oriented. And not all languages are object-oriented. And what is this whole object-oriented thing about? So you should know what this whole notion is about before you start programming in a language that's kind of seeped in the idea. The idea, basically, is that a program is written as a bunch of classes, right? So if you think about, let's back up for a second. If you think about Carol, right? When you were writing Carol programs or you saw Carol programs, you would actually create some Carol program by saying public class Carol program extends Super Carol. Let's just say we're using the Super Carol model. And then you put some stuff in here. You had like your run method in here, maybe some other methods. And what you did was you were creating a class that was basically the information for your program, what instructions you were actually going to execute as part of that program. So what a Java program is, it's just a set of classes. You may have more than one class. Like in Carol, right now, you always just have one class. And inside that class, you may have a bunch of different methods, but you always have one class. A Java program can actually have multiple classes associated with it. And when we start in this class, we'll start with some simple ones that are all just one class. But the idea to think about is that you can have more than one class. Okay? And what these classes are, which you can think of a class as, okay, a class is just basically an encapsulation of some behavior that the program does. Just like in Carol's world, you had some behavior of a bunch of different methods you defined for Carol to actually be able to execute, right? Those are just different behaviors. But you also have some data. So it's behavior and data. Because in the Java world, you're now actually going to keep around track of information that are not just beepers in some world, but they're actually like numbers that you're going to store somewhere, and that's your data. And so what we do is we think of having all the behaviors, all the kind of manipulations you might want to do with data, along with the data, and put that all into this thing called a class. So just like in Carol where you had a class and you had behaviors, you could just imagine, yeah, we're going to have some behaviors, which means in Java we're going to have some class and define a bunch of methods in that class, but we're also going to have some data associated with it, and that whole thing together is going to be a class. Now, it turns out the thing that's interesting about classes, so any questions about the notion of a class? It's just kind of this abstract concept right now. the thing that makes classes really powerful is that classes actually get organized into hierarchies. Let me just draw it here. Okay? And you've actually already seen this in a very small way with Carol. So all the things that you've seen in Carol are going to translate over. Remember we talked about the basic Carol model, and when you were writing a program you could say extends Carol, and when you did the basic Carol model you got like move and turn left and pick beeper and put beeper, and that's all you got. And then we said, hey, you know what, you really want to do turn right and turn around? Well, there's this thing called Super Carol, and Super Carol is just a souped up version of Carol. Well, guess what? Carol was just a class, and Super Carol was also a class, but Super Carol is a class that extends the functionality of the basic Carol class. Okay? So we say that Super Carol, the way we would draw things, if we were going to put boxes around them and draw them like the book, is say that Super Carol is a subclass of Carol. And Carol is the superclass, so this is where it's going to get confusing. The superclass are the things in some sense that are more general, and the subclass are the things that take the basic idea of some class and extend it. So Super Carol does everything Carol does, but it also does turn right and turn around. Okay? So Super Carol is a subclass of Carol, or alternatively, Carol is a superclass of Super Carol, which sounds a little bit backward, but the super here and the super here mean two different things. Super here means sort of above, and super here means cooler than. Okay? So don't think of them as like they mean the same thing. It's just an overloaded term. All right? So you might say, okay, Mehran, this is getting a whole little abstract for me. Well, let me put it in terms that you understand. You're a human being, right? At this point, you should say right. And if you're not, come talk to me. All right. It wouldn't be the first time. So we have humans. Okay? Humans are just a class. Okay? And all humans are primates. Primates are a superclass. Are a superclass of humans, because all humans are primates. All primates are mammals. And all mammals are animals. So there's actually a much deeper and richer hierarchy, say, in biology than there is with Carol. And when you actually see Java, Java will eventually have sort of a richer hierarchy associated with it. Now, the interesting thing about this is not only are humans primates, but monkeys are also primates. Okay? Humans are not monkeys, and monkeys are not humans, so there's not a strict relationship. You might say, well, we don't know about that, but there isn't a strict relationship between humans and monkeys other than they're both primates, and that makes them mammals, and that makes them animals. And the whole notion of having this hierarchy of classes, right? So you could think of being an animal as just a class, and it has some behaviors. What does it mean to be an animal? Well, to be an animal, it means you digest food. Right, that's like not something like sunlight. And actually, one of the technical terms, I'm not a biologist, but this is what my friends tell me, is that embryos pass through the blastula stage. Any biologists in here? Is that right? Yeah. Okay, good. Because I was like asking a friend of mine, like, what differentiates animals from plants? And he's like, well, of course, the embryos pass through the blastula stage. And I'm like, all right, right on. I had no idea. I was like, how do you spell blastula? And we'll just put blastula down here. Right? And so that means, guess what? All mammals inherit those same properties. All mammals also have some internal digestion of food and also pass through this blastula stage. But mammals, additionally, we know are warm-blooded in general, and they have mammary glands, which is what their name mammal, where the name mammal comes from. So mammary glands, or it's just kind of a generalization of sweat glands. But that's what mammals have. And then all primates are mammals, which means all primates have all of these same properties, plus they have more. And so primates, interestingly enough, have 5 fingers. I didn't know all primates have 5 fingers, but evidently I'm told that they do. They have opposable thumbs. And they also have fingernails. But fingernails we just won't put up there. It's not a big deal. Okay? And then we get down to humans and monkeys, right? And humans, it turns out, in theory anyway, we're supposed to have highly developed brains. I'll just put brains in quotes here, okay? Because other animals have brains too, but we're supposed to have highly developed brains. And we have erect body carriage. That's just what we are. We're erect brains. And monkeys have other things that are going on with them. Evidently their brains are not as highly developed, and they sort of like their knuckles drag on the ground. Sometimes I do that in the morning, but that's not important. But that's the whole point. This is the class hierarchy. Okay, so these are all classes. And things that are subclasses of some other class means they inherit all of the behaviors of the things above them all the way up the chain, plus they may have their own additional behaviors. And that's the key concept here of organizing things into classes. And you'll see that in more specific instances when we get into Java. You saw it already with Carol in just a really simple example, right? There was 4 commands for Carol. Super Carol gave you those 4 plus an additional 2. That was it. Okay? Now, besides this idea, there's another key idea that comes up besides this notion of classes. Okay? And that's the notion of the instance of a class. Okay? And what the instance of a class is humans are a class. There is no one person that is, oh, you are humanity, right? You are a person, right? So and what's your name? Wow. Eduardo? All right. So I hope I'm spelling this right. Eduardo. Is that right? Is an instance of human, I would hope, right? So what that means is you're going to have things in your Java programs that you create which are objects. And what an object is, to differentiate it from a class. So Eduardo is an object. Okay, I'm sorry to break it to you. That's just, you're an object. An object is an instance of a class. It is a particular example of a class. There will be multiple objects or multiple instances potentially of some class. And that instance of a class has all of the characteristics of the class and all of the other classes above it in the class hierarchy. So by looking at this, I can say, hey, Eduardo, guess what? You went to the blastula phase when you were an embryo. Good times, because you're an animal, right? And I know that, and this is inherited all the way up. So that's the important thing to keep in mind, is you're going to be writing classes. You're going to be writing things that define some set of behavior. And along with that, you will be creating instances. So this is an instance of the class, and the instances are what we refer to as objects. So all of your instances in the world are just things that we think of as objects, and your classes are, in some sense, the templates for those objects. Okay? So any questions about the general concepts? I know they're a little bit high level, but it's important for you to kind of understand them. Okay? So with that said, let's actually begin to look at this notion in Java. Okay? And so the way that this is going to work,
In Carol, what were the objects?
So in Carol, it turned out what you were actually just creating was a single Carol object was being created that contained your program. And that's what was actually run. So you created the class Carol, and when that puppy actually sort of fired up and you saw a little Carol running around in the world, that was a Carol object that was an instance of your class. Now, you actually didn't see multiple instances there. There was only one Carol instance. So there it's it's a good question because it's very easy to get confused between the instance and the class in that case because there was only one. But in here you'll actually see we'll create classes and we'll have multiple instances of them. But your running Carol was basically the instance of that object. Okay? Question?
So basically, like, you could have, like, several carols running around in, like, one program?
You could if we sort of set it up that way. In the Carol, the way it's kind of set up is it only sort of behind the scenes creates for you this one instance of Carol. But in some alternative Carol universe, we could have actually just taken your class and say, hey, guess what? We're going to just create multiple Carol instances from your class and have them all run around in the same world. We could have. And guess what? That's what seemed to have happened in this room, right? Somewhere along the way, there was this class human, and someone came along and created multiple instances of you. I wouldn't say just necessarily one person, but now there's multiple instances of you, right? And you're all running around the world doing your thing, and you interact with each other. And guess what classes actually do? They interact, or objects actually do. They interact with each other. Okay? So with that said, there's going to be some functionality we're going to use that was written by someone else. So just like Carol, the basic version of Carol was written by someone else. When we start with Java, we're going to start with some set of scaffolding or libraries that were written by someone else that are going to allow us to do a bunch of powerful things in Java very early on. Okay? And this is something that's called the ACM program hierarchy. So it sounds all complicated. But all this is, right, in much the same way that I drew that picture over there with animals, mammals, primates, humans, and monkeys, this is a hierarchy of classes that exist in Java's world, or at least are provided by the ACM. And you might say, who's the ACM? Anyone know who the ACM is? They're big, they're bad, they're nationwide. They're the Association for Computing Machinery. It's the oldest computing society. They've been around actually for about 60 years or so. And you're like, but Mehran, I thought you said hundreds of years. Yeah, before then people called it math. So Association for computing machinery has this programming hierarchy, and what that means is the kind of programs that we write in this class, just like when you wrote your Carol programs, you extend Carol or you extend Super Carol, you're going to be extending different kinds of programs, either a console program, which is something that produces textual output, a dialogue program, which brings up little dialogue boxes that ask for information, or a graphics program that actually draws some pretty funky stuff on the screen. All of those classes are classes that are inheriting from a class, a superclass called program. So all of the things that you write as a dialogue program or a graphics program are all something that are programs. And all programs are something of type JApplet, which just means Java applet. And all Java applets are of some type called applet. Anyone ever heard of an applet? A few folks. An applet is something you can run on your web page, interestingly enough. That's kind of where the term comes from. It's like a lightweight application. It's an applet. It's like an application, but small. And so it turns out, since all of the programs that you're writing are actually inherit the properties of being an applet, they actually will be applets, which means you can put them on your web page and run your programs on your web page if you want. Later on in the class, we'll talk about how to do that. Okay? But you're going to go, and in this class at least, you're not going to write anything that directly extends like JApplet or applet or program. Everything you write is going to extend down to this level, but it's important to know there's different kinds of programs that you can actually write at that level. So let's look at an example of a Java program, and I'll show you your first Java program today, so we can feel good about Java. No, it's not that one. It's this one. It's small, it's tiny, it's fun, it's Java. All right. So let me expand this whole thing out so you can see the whole program still fits on one screen. Okay? And you might suddenly notice there's a bunch of things in this program that look very similar to Carol. That's because Carol was implemented in Java. So the first thing you want to look at here is we have a file called helloprogram.java. Just like your Carol programs were written with a .java file, you were creating a .java file here. This is a source file because it has source code in it. Up at the top, we have a comment. G uses exactly the same structure as Carol comments. Yeah, because Carol comments were actually Java comments. Comments in Carol and Java are exactly the same. Just like you imported Stanford.carol.star, now you're going to be using the stuff that the lovely folks at the ACM have provided for you. So you're going to import acm.graphics.star and acm.program.star. What are these things? These are just, I won't back up because we're not on the slides. These are just, remember I said you write your classes and someone else may have written some classes and they all get linked together before they're executed? These are just some other classes that someone else wrote that are going to get linked into what you do. Right? They provide you the definition for things like what a graphics program actually is. So now what you're going to do, as we talked about, all Java programs are just a collection of classes. So just like in Carol, we have public, class, and some name for your program. Here we'll call it Hello Program. And a Hello Program is a particular kind of program. It doesn't extend Super Carol because it's not a Super Carol program anymore. It's going to be a graphics program. It's actually going to draw some stuff on the screen, so it's going to extend the graphics program. But all the boilerplate should look the same, right? That's why we had you do Carol, because all the stuff from Carol just translates directly over to Java, except now we're sort of cooking with gas. Now we're doing the real thing, okay? So it extends graphics program, and guess what? Inside here we have a run method, just like Carol, and that's where the program begins executing. Now where things get funky is you're like, oh man, what happened to pick beeper and put beeper and move? Like life was so good, it was easy, turn right was like the extent of it. What is this, like add new glabel hello world? Like what is this all about? Okay? We'll go through this step by step. All this is saying is when you create a graphics program, we'll go through the details in just a second, you're going to get a blank screen. You're going to get an empty canvas in some sense. You're going to be an artist and you're going to draw stuff on that campus. And the thing that you're going to draw on that campus is some label, and all that label is just basically words, and the words are going to be hello world, because you want to write hello world on the screen, and you want to write it at a particular location on the screen. The location on the screen you want to write it at is 100,75, and I'll tell you where that is on the screen in just a second. And then once you create this little label, you're going to add it to your canvas. You're going to say, I have some canvas, plop that puppy onto my canvas. Okay? So let's run the program, and I'll just plop it onto the canvas for you, and you'll see what's going on. Life will be good. So we run this program. Drop the microphone. Drop the microphone again. Alrighty. So we want to do hello program. We're getting excited. We're running. The disk's just churning away. And there's your first Java program. You're all Java programmers now. What did you do? You created a graphics program which brought up this big window and said, I'm blank canvas, draw on me. And you said, all right, hello world, woohoo! And I'm done, because that's all you did. You said, here's hello world, put it up on the canvas for me at a location 100,75, and thanks for playing, that's all I'm going to do. But now you've actually gone through the whole process of compiling your Java program and turning it into this intermediate code, and the intermediate code gets executed, and you actually did something. And that's like half the battle right there. The next 9 weeks is the other half of the battle, but half the battle is like getting this up. I kid you not, really. If you can make that happen, you're just most of the way there. So let's do something a little bit more exciting. Let's actually do some interaction with the user. Let me show you another program. Remember, this one is a graphics program. I told you there's a bunch of different kinds of programs you can have when I showed you the picture, right? So we had a graphics program. Let's look at something called a console program over here. No, not in Java. So you're always extending one kind of program. And a graphics program will actually, as you saw, you can put up text. A console program is just meant to be a textual program, so you're not going to do any drawing. But here's another program, right? Again, a lot of the same things as before. You have some comment up at the top. You have some libraries that you're going to import. In this case, you're not doing anything with graphics, so you don't need to import acm.graphics.star. You just need to import acm.program.star, which just says, get me all the standard stuff for a program. If you're doing graphics, you also need to have a second line for acm.graphics.star. If you're not doing graphics, you don't. So again, public class, this one's called add two integers, because guess what? It's going to ask the user, very exciting program, for two integers and add them together. But in fact, it's going to do something interactive with the user, which is pretty exciting in itself. This is going to extend a console program, because it's not going to have any graphics. Oh, yeah, I know, it's sad times. But sometimes text is very powerful. What's it going to do when it runs? It's going to write out to the screen, and this time we're going to use something called println, which is just, we like to drop some vowels here and there, which stands for print line. And it prints a line. This program adds two numbers. Then it's going to read an integer from the user, and we'll go through all this stuff in more detail. Don't worry, this is just a high-level overview, so you get some basic idea of what Java looks like. It asks the user for n1, right, because we have to be very scientific. So rather than give me the first number, we say enter n1, right, and suddenly we're much more formal. Enter n2, right? And so what this is actually doing is asking the user for a number, and whatever number the user gives us, we stick in this location called n1. And whatever number the user gives us here, we're going to stick in a location called n2. And we'll actually talk about what these locations are and how they get set up and everything next time. But I just want you to see something before we kind of go into all the details, because we've got to start somewhere. Then we're going to add n1 and n2 together and store them in a place called total. And then we're going to write out the total is whatever the total is, and then a period, right? So this is in some sense the world's most expensive calculator that adds two numbers. And we'll go ahead and run it. Add two integers. We're compiling. We're feeling good. And that's the program we want to run. And now this comes along, and notice, now we have some window that rather than putting graphics all over and telling it where to display some words like hello world, we just said write some line. And so what it's going to do is just sequentially write lines on the screen, because this is what we think of as a console. All a console really is, the way you can think about it, is it's a window that contains text and can potentially interact with the user. So there's places where we might ask the user for input. So we said this program adds two numbers. I hope you can see this in the back. It's tiny, tiny font. Enter n1, and it's sitting there with the blinking cursor. And anytime you see the blinking cursor, that means, hey, I'm expecting some value. So give me some value. What's some integer? 12. Someone said 12, someone said 1, so I'll take 12 as n1. Then it asks for n2. I'll give it 1. And lo and behold, it says the total is 13, period, end of program. Okay? At this point, there's a blinking cursor, but the program is done. But now you've just seen a real Java program that actually takes in values from the user, computes some, does some computation on them, and displays output. Okay? And this is a console program as opposed to a graphics program, because all the stuff we're doing here is textual. Okay, so any questions about the basic idea of classes or objects or these different programs we're writing? The programs that are running, when they run, they are objects. They're instances that are being run for you. What they're doing as instances, they're objects that are inheriting all the behavior from the class template. And then when we run, an instance is actually created and it's run.
Why do you always import like graphic program or program? Why don't you just import the biggest category within it, which would be acm.star?
Because if you say acm.str, strangely enough, you won't necessarily get everything underneath ACM as well. You'll get everything at that level. So there's actually a package for ACM, and there's a package ACM graphics, and there's a package ACM program. And what you really want is everything inside ACM program and ACM graphics, not just the things that are in the ACM package by itself. Yeah, it's kind of it's an interesting technical question, and if you don't need to worry about the details, just add both of them and you'll be fine. No, the console program you just print out. That's one of the differences with the graphics program. I should actually set you both up. With the graphics program, you have to tell it where stuff goes. Console program is just writing out line by line. Sorry. Yeah, every time you run a Carol program, you can think of what it's doing as creating an instance of Carol, which is that little guy you see on the screen, and he's going around and doing stuff. So in Carol, there was always only one instance of the object. Here you'll actually see we'll create some objects where we can have multiple instances of an object in the same world, and I'll show you some examples of that in just a second, but we just haven't gotten there yet. Okay? So what we're going to do now is we're going to think a little bit about graphics that we can actually draw. Because in the graphics world, it's easiest to see multiple objects. We're going to put multiple stuff up inside our little graphics canvas. So what's this whole graphics thing about? Let me tell you a little bit about the graphics window, and then we'll put a couple different objects up in a graphics window, and you can see what I'm talking about. So in terms of graphics, all graphics that we're going to do are a model called a collage model. And if you remember in the days of yore when you were a wee tyke, did anyone have like a little felt board with little felt animals that you put on it? Yeah, that was a collage. Or if you had a big piece of paper and you had some like crazy, or not crazy glue, it was, what was that? It was glue stick. Don't smell that stuff too much. But you like would take some piece of paper and you're like, oh, here's a picture of a cat, and you would like put some glue on the back of it and put it up on there. And then you say, oh, here's a picture of a dog, and put some glue on there and put it up on there. That's the model for graphics in Java. We're going to have these little pictures or little objects, and we're going to say show up here, and show up over here, and show up over there. So what you have is a collage which starts off with a blank canvas, and you're going to put objects onto that canvas. Okay? And so what we can do is create various kinds of shapes or pieces of text and put them up in various places on the canvas. And you just saw an example of that with Hello World, but I'll show you some of the other things that you can create. The different kinds of objects that exist in the graphics world, one you just saw, it's called a G label, for a graphic label. This is just text in some sense. It's text that you can put up somewhere in the world. There's also a G rect, which is a rectangle, oddly enough. A G oval, which is an oval, or if you actually make the height and width the same, it becomes a circle, right? So that's why we don't have circle, we have oval, and same thing with rect versus square, because all squares are rectangles. And G line, which just means a graphic line. So these are the different kinds of objects we can have. These are classes. They are templates for objects. We're going to create particular instances of these objects and put them up in the collage. But these just tell us the kinds of things we can have. They're the general class. So if we come back, if we close this guy, and we come back over here to Hello Program, what we've done is we've said, I want a G label. G label is the class. When I say new G label, what that actually does is says, give me a new instance of that class. Give me an object that is a G label. And the things that you're going to specify about that particular instance are it has some text associated with it, which is hello world. We put all the text inside double quotes. Okay? So hello world without the double quotes is actually the text that's associated with this label. And we give it some location, 100,75. So now this little object, okay, which is an instance of a label, it says, hey, I'm one particular label in the world. And the kind of label I am, I say hello world, and I'm at location 175. And it's like, okay, you have this label. What are you going to do with it? And I'm like, put it on the canvas. And the way you put it on the canvas is you say add. So in all graphics programs, when you say add, there is something that you will specify to add. The things that you are specifying to add are instances. They are individual objects that you're going to put on the canvas. And the way you get those individual objects is you create a new version of some particular class. Okay? So this creates that new label at location 175, and when it gets added, it gets put up there. Now, there's other kinds of things we could do with this. So if we kind of return over here. Oh, this is just the add two integers program. Let's do add two integers real quickly. Yeah, 17, 25, 42, writes out 42. Same thing you just saw, except now in excruciating detail. Let's say we want to do something that makes a G label more funky than we originally had. Okay? So again, we're going to have our hello program that's going to extend the graphics program. And here we're going to do things slightly differently. What we're going to do here is we're going to create a new instance of a G label object. So we say new G label, and again, we're going to name it hello world and 100,75. So I have some label that's hello world at location 175. And I say, hey, you know what, label? I want you to look different than you actually are. Okay? So now that I have this object, I have this little label. You can think of it as a little object that sits somewhere in the world. It's not being displayed yet because I haven't added it yet to my canvas. It's being stored somewhere which I've named label. Okay? And we'll talk about this notion of G label next time. But it's something I've created called label, which is just a new instance of this hello world label. First thing I want to say is, hey, you know, I want to change what the font looks like. Anyone know what a font is? Right, you've probably used different fonts in your word processor. It's just the way characters actually appear on the screen. It's a term that comes from typesetting. I want the font to be sans serif 36. So what happens when I start off is I say, create for me a new label that's name is hello world. And so it says, okay, I have some label object. The label, the words that are associated with that label, hello world. Notice there's still nothing on the screen. Here's my screen. This is my canvas. This is all in the computer's memory somewhere. It's just saying, yeah, you've created some label. You haven't displayed it yet. You've just created it. And I say, hey, I want to tell that label to change its font to sans serif 36. The way I do that is I have an object that I've created. The object is named label. I use the name of the object followed by a dot, followed by a method that I'm going to call in that object. Remember, in Carol's world, we had methods. The way we called Carol's methods was we just gave the name of the commands to go execute that method. Now, all methods are associated with objects, at least for the time being. So when I have label and I say set font, what that actually means is set the fonts for this particular label object to be sans serif 36. And so when I execute that, what happens is it becomes 36-point font in sans serif, which means serifs are just little things at the ends of, if you can see the font up there has the little, swishies at the end of the letters. Those are serifs. So a font like this doesn't have any of the swishies at the end of the letters. It's sans serif. Sans means not. Okay? Then we say, you know what? I'd really like you to be red because black is just so blasé and red is really the new black. So set your color to be the red color. And I go, okay. So I execute that and it turns itself red. There's still nothing on the screen. This is all kind of with the label. And now that I've taken this label and I've taken its text and made it big and turned it red, I finally say, hey, graphics program, add this label, add this object to your collage. And it says, okay. And it adds it at the location at which this label was created, which was 100,75. So then it finally shows up on the screen. It only shows up on the screen when I actually do the add. Up to that point, all I've done is modify some of the properties of this thing. Okay? So starting next time, what we're going to actually get into is thinking about what is this G label thing about? What does it mean when we actually specify a method for an object, and go into all of that in a little bit more detail, but hopefully you've seen an example of what your first Java program looks like. All right, I'll see you on Wednesday.